Started section 3.3 last time. We're looking at increasing and decreasing functions in the first derivative test. So a couple of real quick reminders before we get jumping back in with examples. We talked on this screen, not this one, the next one, about the fact that increasing functions have positive first derivatives, okay? And decreasing functions have negative derivatives, right? So we can identify if something is increasing or decreasing by deciding if the sign on its derivative is either positive or negative. And then our first derivative test talked about what happens when signs change. So when the sign of the derivative changes from positive to negative, we have a maximum. And if the signs of our derivatives change from negative to positive, we have a minimum. And we had done two examples, I believe, where we had identified locations of being increasing and decreasing. Sound good? Okay. So the example that we're on, number 3, is going to have us delve a little bit further into this by using the first derivative test to decide where we have those maximum minimum values as well. So A, on the directions, say to find the critical numbers. Critical numbers, remember, are places where the derivative is 0 or doesn't exist. B has the intervals where the function's increasing or decreasing. Those two pieces were what we did last time. C is the part that's new, applying the first derivative test to decide where we have maximums and minimums. And then on D, we actually did some of D last time as well. It was asked about in class, like, what does this look like on a graph? To confirm that the graph matches what we found from our calculus techniques, okay? So our example here is a very simple simple function that you're familiar with, starting that way on purpose, right? You basically know what this graph looks like. What is this a graph of? It's a parabola. Tell me something about this parabola that's helpful right now. It's opening downward, right? So you know already, that's not a good color, let's try that again. You know already that it has this basic shape. It's going to be increasing on the left, it's going to be decreasing on the right, it's going to have a maximum point on it. You know all that, right? So as we do all of the calculus to support that, if that isn't the way the answer turns out, we're going to know we made a mistake. Make sense? Okay. So the first part of this is to find critical numbers. In other words, we need to find where the derivative is equal to 0 or does not exist. So what is the derivative of this function? Negative 4x plus 4. Everybody good with that? Wonderful. Now, I need to set it equal to 0 or does not exist. This one doesn't have any does not exists. Does not exist occurs in two locations. We'll see it happening. Either when we have denominators, that could be 0, or sometimes we'll have radicals, right? You can't have a square root of a negative number in the real number system kind of thing. That's sort of the less pronounced case. We don't have that happen as often. But those are the only cases where we have to worry about the does not exist. For this one, it's just going to be equal to 0. And where does this equal 0? Negative 1 or positive 1? Positive 1, yeah. So it's a positive 1. So do a little bit of algebra, eyeball it either way, whatever. If you put in 1, this is going to be equal to 0, right? So there's only one critical point. All right, so that's the first step. The second step is where we draw the number line. And as promised last time, they don't always create 4 intervals. This time I only have one value, 1, so I only have 2 intervals. I have the interval to the left of 1, and I have the interval to the right of 1. And I choose values on either side. So what's a nice value you might want to choose on the left-hand side of 1? Negative 3 or 0 or whatever, right? So I think zeros are easiest, but you can use whatever you'd like. We talked about that last time. What would you like to pick on the right-hand side of 1? 2. All right. So we take these values that we've chosen in these intervals, and we put them into the derivative. So we put them into here. And what we want to know is when I put the value in for x, do I get an overall positive number, or does the answer give me a negative number? So if I put in 0, what do I get? Positive. So it's going to be increasing. We'll get there in a second. If I put in 2, what do I get? Negative. Okay? So as mentioned again before last time, increasing and positive go together. Decreasing and negative go together. So I can identify that this is increasing from negative infinity to 1. Remember, we're using parentheses on either side of those. And it's decreasing from 1 to infinity. Now, this matches with our expectation over here, right? So it indicates that we're at least on the right track. That doesn't mean for sure that we've got the right answer, by the way, right? But it at least goes along with the intuitions that we had to start with, and that's a good sign. All right, step 3 then was to decide whether we had maximums or minimums. So in particular, right here in the middle, what's going on? It's got a peak, right? There's a maximum there. That's what the first derivative test tells us. So we have a maximum at x equal 1. Now, it's possible that the question's asking simply what x value we have a maximum at, but it's also possible that it's asking what that point is. And x, y is the point, but this is only x, right? So we can also say this happens at the point 1 something. How do I find the something? Plug it into the, right, what we're saying? Into the original, you bet. So I take my original function way back up here, and I put in the number 1. So if you put in the number 1 here, what will you get? Yes, 5. So pay attention to how the question's asked. This one says, apply the first derivative test to identify all relative extrema. A relative extrema occurs at a point. So if this were the directions, the point would be what I would be writing down. Okay? So it would be the 1, 5. But there might be slightly different directions that just simply ask you to identify the x value to. D. All right, so D, we're going to grab a calculator. We already know what this basically looks like because it's a very familiar to us kind of equation. But we're going to verify the specific location by using the calculator. So grab it if you have it. And remember, we're putting in the original graph that we were given. And I'm doing zoom 6, which is the standard window. So it has the same basic shape that we already identified. And if we take a look at it maybe a little bit more carefully, this is my peak right here. And it does look like it's lining up at about x equal 1. Okay, if you wanted to trace it to be more certain, you certainly could do that. There's actually another kind of cool feature, I'll mention it since I've got the calculator screen up, that you can verify with. If you hit math, let me zoom out so you can see what I'm hitting the buttons wise. There's a button here that says math. If you hit math, there's a button further down that actually says, I think it's, no, it's not in here. I take it back. It's go back to your graph. It's inside of the calc menu here. Well, it says CALC. So you hit second calc. And it's right here. The number 4 says maximum. So you select number 4 maximum. It gives you some prompts. It says left bound, which means you need to be on the left-hand side of the maximum. So I am over here. And then it says right bound, so you scroll to the right-hand side of that maximum. And then it says guess, which means just get close to the maximum. And it will actually tell you both the x and the y down here. Do notice it's got a numerical approximation problem right now on my screen. Yours may not. Calculators do that sometimes. They are not perfect, right? So this is the value 1, even though it doesn't quite look like it, and there's my y value of 5. So you can also verify your location with the calculator that way. Is that cool? It's a good verification thing. Okay, we'll try that on the next one too. Okay. Let's go back and do number 4. So let me just drop this into the graph since we do have a few people gone today. It looks like this. Okay. All right. Next one, number 4. Same directions, but this is a far less familiar to us kind of an equation, isn't it? Yeah, it's a third root, so it might help you to sort of remember that too. This is a cube root graph. Again, you may or may not, whoa, that wasn't what it's supposed to be. Let's try that again. You may or may not know what this looks like, but it kind of looks like an x cubed graph on its side, like laying down. And then the +1 shifts it. It shifts it to the right. So we're going to have some differences to this particular graph that the other one didn't have. We're going to go through the same steps. So step number 1 is to find the critical values. So we're going to find where the derivative is equal to 0 doesn't exist. Now, the version that it was given to us in, x to the 1/3 plus 1, is actually the easier way to do the derivative than the changed one that I sort of intuitively said, what does this kind of look like, right? So I need a derivative of x to the 1/3. What is that? Good, 1/3, x to the negative 2/3. And then the derivative of the 1 would be 0. It's going to go away, right? Okay, so if we sort of adjust this, manipulated it to something that looked a little bit more like the way that I've manipulated it at the beginning, the cube root of x, because it's negative, it will move to the denominator. The 2/3, the over 3 becomes a cube root, and the 2 looks like this. Does everybody remember that from an algebra course or a pre-calc course? Okay. It's easier if it's more familiar to us, and as much as you may not like radicals, they are more familiar to you than negative exponents, and especially negative fractional exponents. So this is an easier way to think about this. What about equals 0 equals does not exist? Do you notice? Okay, so it's equal to does not exist at 0, right, at x equals 0. What about equaling 0? It doesn't. Sophia's right, it doesn't. It just doesn't ever happen. In order for a fraction to equal 0, the numerator has to be able to equal 0, but my numerator is just a constant 1. That can't happen. So it's not going to equal 0. I'm going to get only a does not exist value at the x value of 0. So once again, I've created an interval, so I'm on to part B, that only has, well, a number line that only has 2 intervals, before 0 and after 0. Now, you might be looking at this and saying, but can you even use a negative? And the answer is that you can. You can for a couple of reasons, actually. The biggest reason that you can use a negative is because it's actually a cube root. We can take negative cube roots. That's fine. Okay? But not only that, but what happens when I put a negative into x squared? It becomes positive as well. So there's actually 2 reasons why negatives are perfectly fine here. Okay? But it is something to sort of be aware of when I have radicals show up. Can I even use a negative? Because I can't always, right? If this had said the square root of x cubed, I would have a different scenario. There are negatives, and I couldn't use them. So I can use negatives. We need a number before 0 and after 0. What one would you like to pick? Oh, I like -1 and 1. They're good numbers. Okay, so go back to the original equation. The x, and I would think of it like this. That's the one I would be using. If I have the cube root of -1, I didn't mean that one. I take it back. This one's the one I wanted. I was already ready to do the ordered pair point. This one's the one I want. If I have the -1 in here, so do -1 squared, I take the cube root and multiply it by 3, and then I do 1 divided by it, right? All those pieces together. Do I get a positive or do I get a negative? I get a positive. What about the number 1? Also get a positive. Okay. We haven't seen one of those in our examples yet. All 3 of the other ones kept oscillating. We went positive, negative, or negative, positive. Right? We didn't have that happen. So this one is, in fact, going to be increasing from -infinity to 0, and again, from 0 to infinity. Now remember, we talked about the fact that we have to put the 0 in and not include it. The ones that we looked at last time where I mentioned it because we had this location where it had an asymptote. I think it was on example 1. Yeah, there was actually an asymptote at x equals 0 that separated it. I don't have an asymptote here, but I still have a does not exist. So we'll talk about what that actually is. But I still have a does not exist. So there's still that location in the middle where it's neither increasing nor decreasing. It is 0 in that spot, okay? Or it does not exist, in that spot. So we do have to separate this. How about maxes and mins from this information? Verbalize for me, Sophia. You're shaking your head just perfectly. What do you have? There's none. Right? There aren't any maxes or mins. Because it doesn't change from positive to negative or negative to positive, right? So when that happens, what we literally have is that something's increasing and then it does something and then it keeps increasing after that. There's not a max or a min there, so I don't have any maximums or minimums. So let's look at this graph because it's a very interesting one. that's far less familiar to us than the previous one. Feel free to use your calculator and put it in as an x to the 1/3 if you wish. There's also cube roots underneath the math button. It really is under math this time. So if I click on math, number 4 is a cube root. So you can use cube root of x if you wish, and then plus the 1. Okay, so my window being from -10 to 10 is okay. I want to make it a little bit smaller because it'll be easier to see what's going on if I make it a little tighter. So I'm going to go -5 to 5. I think that'll be sufficient. If you graph it in the other one, you're just going to want to zoom in because you'll feel like I don't quite see what's happening. Okay. Do you see how it looks like that cube root graph flipped over on its side, like laying down? And it's shifted. It's actually shifted up. I mentioned right. I was wrong. It's shifted up because this is shifted up one. So what's happening right here at 0? Can you tell me what's going on right here? It's something we talked about back in section 2.5, so it's been a minute. What is it? The slope, so say it louder for sake. The slope is undefined. So when do we have slopes that are undefined? What kind of lines create those? Vertical ones, right? So this location right here is creating a vertical tangent line. There were 3 places where we talked about derivatives not existing. One of them is asymptotes, which includes like disconnected pieces, right? Jumps or holes in the graph, right? Disconnections. One of them was sharp turns, right? And then one of them is vertical asymptotes, and we finally have now seen an example of a vertical asymptote. There is a vertical asymptote on the y-axis here. If you were drawing tangent lines, that's what we would draw as a vertical line there. So that's what's happening with our graph. So over here, as we're verifying it, just for the purposes of it being in your notes for later, you have something that looks like this. And this isn't a great example picture, but it's sort of the right idea. You might even make a note that if you've drawn it poorly, like I did draw it very great, there's a vertical tangent line here. So this is an example where it's a lot more difficult to just look at a calculator and skip all the calculus and assume that you know what the answer is. Because the graph, even when you looked on the calculator, you might have looked at it and thought, well, it just looks like it's increasing over the whole thing. And it kind of did. It's really difficult to actually see a vertical tangent line location. So it's not quite as simple to just skip the calculus and be able to give all the answers like maybe the last example was. Okay? All right, we have one more in this lesson. Okay, directions say to consider the function on the interval 0 to 2 pi. It's doing that because I have a trig function. We talked about that last time, right? How trig functions, they'll isolate like an interval that they want us to look at usually because it continues to oscillate a lot of times. You're going to find the open intervals where it's increasing, decreasing. So part A on this one includes what we did on A and B on the last one. Directions are just described differently, but it's including A and B pieces. So you're going to find the critical points and the increasing, decreasing in this one. And then part B is what part C was before, right? We're going to apply the first derivative test, figure out our maxes and minimums, and then part C is the same as part D was before. We're going to confirm it with calculator. Okay? So directions are outlined a little differently, but they really still include all the same pieces, except for the 0 to 2 pi. That part's different because it's trig. So step 1 is to do the derivative. So what's the derivative of x plus 2 sine x? So maybe it's about saying 1. 1 plus what? 2 cosine x. Okay, 1 plus 2 cosine x. And what do we want to do now that we have this derivative? Set it equal to 0. So this is almost like we could write out steps, one right after another. They're all the same, okay? I've been working on some algebra stuff with my 9th graders, and every single problem is the exact same steps over and over and over again. It's just like that right now. Just the same steps. This one feels a little different, though, because it's trig at this point, right? So solving trig is a little bit different than solving algebra. So we're going to move the 1. So 2 cosine of x is negative 1, and divide by my 2. So cosine of x is negative 1/2. All good? Okay, this requires us to think unit circle, right? I got to think about the unit circle. So let's take a look and we'll draw it on the screen. My unit circle. And I want the cosine value to be negative. So let's first identify where in the 4 quadrants is cosine negative. 2 and 3. So cosine is negative when the x values are negative. So I'm going to be in quadrants 2 and 3. 1/2. So it needs to be an x value of 1/2. Well, an x value of 1/2 are the ones that are going to be closest to the y-axis. So it's the one that's sort of up here really nearby and the one that's down here really nearby. Okay? Do you remember what this angle measure is that goes around here to here? It's got to be the over 6s or over 3s, right? What is it? Remember when I think about thetas, like angles. So 4 pi over 6 would be what? 2 pi over 3. Is that the one we want? Okay, is that all right with everyone? 2 pi over 3? If you're like, I don't remember, you can check it real quick. Grab your calculator. As long as you're in radians, grab your calculator. Type in cosine of 2 pi over 3. Did it give you negative 1/2? Wonderful. So you can use your calculator to check too. Okay, good. What about the next one? All the way around here. So remember, if it's an over 3, it's still going to be an over 3. Okay, so what was it? 4 pi over 3? Okay. Oh, sorry. I wanted to use the same color. Orange was not my best choice, but that's okay. 4 pi over 3. Can you still read it? Maybe enough. Okay, so it's 4 pi over 3. Check it again. If you put in cosine 4 pi over 3, does it give you negative 1/2? Okay, excellent. So you can use your calculator to confirm your unit circle remembrances or maybe uncertainties, right? Okay, so those are our 2 values. I don't need any others because while sine values and cosine values do this still cyclic thing, I was relegated to only being between 0 and 2 pi, right, at the very beginning. So I really only need 1 rotation around my circle to check for, and I've done that. So my angle measure, which we're calling our angle here x, is going to be at 2 pi over 3 and 4 pi over 3. Okay, everybody good? Once I get the values, I create my interval. But my interval is not open-ended like the previous ones. It's between 0 and 2 pi because it was told to me to do it that way. And then we have 2 values in here in order, 2 pi over 3 and 4 pi over 3. And we need numbers between them. Okay, so somebody just tell me, what is 2 pi over 3 approximately? I don't have this one in my head, so just grab your calculator. It's about 2. Okay, so it's about 2. So I need a number between 0 and about 2. 1 would be a good one, right? What's 4 pi over 3 approximately? It's about 4, right? People are getting these values if you're like, how'd they do that so quickly? Pi is about 3. So 3 over 3 is going to give me the 1. So that's why they're giving me the 2s and the 4s, okay? So this one's about 2 pi over 3. 4 pi over 3 is about 4. So a number in between would be a 3, would be nice. And 2 pi is about 6, right? So I need something between 4 and 6. 5 would work. Okay, so we're going to grab a calculator, and we're going to let the calculator do the values for us on this one because I chose values that are not friendly in terms of plugging them in, at least in terms of plugging them into a unit circle sort of perspective in our mind. We need the derivative written in here for the moment. Okay, we'll do the original function later, but right now we're talking about the derivative. So I have 1 plus 2 cosine of x. And in my table, I'm going to put in the numbers that we just picked, 1, 3, and 5. So I have that at 1, it's positive, at 3, it's negative, and at 5, it's positive. Trig functions often, but actually algebra functions often oscillate too. So oscillation is sort of our expectation typically. The more rare case is what happened on the last one where it doesn't, and we have 2 that are the same in a row. All right, so let's identify increasing, decreasing. So it's increasing on this first piece, 0 to 2 pi thirds. And it picks back over here on the ending piece, 4 pi over 3 to 2 pi. Okay? And then it's decreasing in between. So 2 pi over 3 to 4 pi over 3. Look, I haven't utilized my screen very well on this one, sorry. All right, part B is identifying the maxes and the mins now. So there are two locations where it changes direction. It's positive and then negative, and then positive. So right here at 2 pi over 3, what's happening? It's a max, yes. So it's a max at, and I'm going to write it as the ordered pair because that's the most specific kind of question that I need. I'll find the y value in a second. So it's a max at 2 pi over 3. And then what happens on the other one, of course, is that it's a min at 4 pi over 3. Okay, so while it's really tempting to say, well, let's just put 2 pi over 3 and 4 pi over 3 into the calculator, into the original equation, it's not going to work very nicely. And the reason it's not is because one component of it is algebraic, it's x. The other component is trig. So one piece is going to have pi's in it, and the other piece is probably going to have radicals, or at least might have radicals in it, right? So we're not going to be able to find an exact answer from our calculator. We can confirm it with our calculator in a moment, but we can't find an exact answer. So we're going to have to get that by hand. So we're going to take each of those and put them in one at a time. Okay, that's not what I meant to do. Let's try again. So we're going to put in to the original function 2 pi over 3. So it'll be 2 pi over 3 plus 2 sine of 2 pi over 3. Okay, now when we looked at the unit circle, we found that the cosine value at 2 pi over 3, well, we were given that the cosine value at 2 pi over 3 is the 1/2, or negative 1/2, right? What's the sine value here? It is. And is it positive or negative, Braden? It's positive. I'm above the x-axis. Remember, sine values are the y values. So this is actually 2 pi over 3 at the beginning, and it's plus a 2, and then this is at square root 3 over 2. It's not a very pretty value. And the best I can do to simplify it differently is that it's 2 pi over 3 plus square root 3, right? It's just ugly. So up here, that's the value that goes in here. It's 2 pi over 3 plus the square root of 3. I had Calc 3 students bemoaning the fact that WebAssign does not like you to put in decimals for stuff like that this week. Actually, it wasn't Calc 3, it was Calc 2 students. I was in somebody else's classroom. So be aware, it's probably not going to let you give a decimal for this. You're going to have to put it in by hand, okay? The other one, very similar. We're going to put in 4 pi over 3. So we have 4 pi over 3 plus 2 sine of 4 pi over 3. All right, so what is the sine value at 4 pi over 3 down here? It's just the same thing but negative, right? Yeah. So it's negative square root 3 over 2. So my value ends up being 4 pi over 3. And then it's minus the square root of 3. So 4 pi over 3 minus the square root of 3. So I've got kind of a mess on my screen, but this is the answer for part B. All right, so let's take a look at the graph because this is an interesting graph. We don't normally look at graphs that combine algebra and trig within the same graph. So you'll be maybe a little bit less certain of what it looks like. So we're going to put in the exact equation we started with, not the derivative, x plus 2 sine x. And I'm supposed to be going from 0 to 2 pi, so my window needs to do that. Window is from 0 to 2 pi. I may not know exactly what my graph's y values need to be, so I'm just going to leave it at the -5 to 5 I used on the last one, and if I need to adjust it, I will. Okay? So we're going to graph it and see what we have. That's not a bad graph. I'd kind of like to see it go up a little bit higher, so I'm going to do that. I'm going to make my window go up a little higher on the y to like 10. So you see the oscillatingness that's coming from the sine part, but you also see sort of the progression that it's moving uphill from left to right. That's the y equals x part that's taking over. So they're both interplaying with one another. And we could actually trace to see this location. We'd get a decimal for it. And the same thing for this location where these maximums and minimums are. And we could see if that decimal mirrors what we would get if we took 2 pi over 3 plus square root of 3 and found its according decimal, right? It's approximation, and we could do it that way for a verification. We can also see that this is increasing, decreasing, albeit slightly, and then increasing again, which matches what we had written down before. All good? All right.